Welcome you all here again to our second day on this mini course about generalized complex structures on flag manifolds with Carlos Varea. So go ahead.
Thank you, Leonardo. Hello, everyone. Today we will continue with our mini course about generalized complex structures on flag manifolds. In the first day, we saw some preliminary concepts. More specifically, we saw the first definitions of generalized complex structures and some results. And we also fixed some notations and defined what is a flag manifold. Okay, and today the idea is to study the generalized complex structures, well, the generalized almost complex structures on flag manifolds. So we will see that we have some kind of root space decomposition in these structures, and then we will classify them, well, at least the almost. Today we are not going to worry about integrability. The integrability will be studied in the last day. Maybe classification, maybe here a better word is a description of these structures. Okay, so this is the idea today. So just remember, we defined a generalized complex structure on a smooth manifold M. We had two ways to look at the generalized complex structures. One is look the generalized complex structure as an endomorphism on the tangent bundle plus the cotangent bundle, satisfying two conditions: a complex condition, the J square is -1, and a symplectic conditions, that is the J star is -J. And another way to look to the generalized complex structure is by means of a maximal isotropic subbundle, no longer on the tangent plus the cotangent bundle, but now in its complexification, satisfying the condition of real index 0, which means that satisfy this condition here, that L intersection with its conjugated is 0. Okay, so this is the definition that we are use today. We also set what is a flag manifold. We saw that a flag manifold is a homogeneous space given by a Lie group over a parabolic subgroup. And also we saw that we can identify it as a compact real form of G, denoted by U, over a maximal torus. Remember that we are considering only maximal flag manifolds here. This is why we have this maximal torus here. Okay. Well, we also saw that since U is compact, the flag manifold is a reductive homogeneous space. So we can decompose the Lie algebra of U as the Lie algebra of T plus its orthogonal complement. And by the construction that we saw on the first day, M is actually the sum of U alpha, with alpha running the positive roots, where U alpha is the real spanned by the elements A alpha and S alpha, which are defined in terms of the Weyl basis. Okay, and we also comment that this orthogonal complement will be identified with the tangent space at the origin of the flag manifold. So the main goal today is to describe the invariant generalized complex structures on the flag manifold. And by invariant, we mean invariant under the isotropy representation. But again, since we have a reductive homogeneous space, we have we can identify the isotropy representation with the adjoint representation. Okay, and also since we are looking for invariant structures, we can reduce the problem to the origin, to the origin. So we reduce the problem of study the whole tangent bundle plus the cotangent bundle, and now we are going to look just to the tangent space at the origin plus the cotangent space at the origin that we are identifying with n plus m star. Or equivalently, we are going to describe the invariant maximal isotropic subspace on the complexification of this space here. Okay, and I finished the first day with this proposition that basically saying that a maximal isotropic subspace on m plus m star can be decomposed in terms of the root spaces u alpha plus u alpha star. And the maximal isotropic subspace L, or L is maximal isotropic if and only if each part of this that I call L alpha is maximal isotropic inside this guy here. Okay, I finished with this, and this is one of the key propositions, because when we pass from this notation of maximal isotropic subspace to the notation of endomorphism, the notion of endomorphisms, we have that an invariant generalized complex structure on a flag manifold can be decomposed in blocks in the diagonal, where each of these blocks is an invariant generalized complex structure on the space U alpha. So what we have, we start studying structures on the tangent bundle plus the cotangent bundle. By invariance, we reduce this to the tangent space at the origin plus the cotangent space at the origin. And now we are reducing our problem to study each of these blocks J alpha case, which is an invariant generalized complex structure on the space U alpha. Remember, again, that U alpha is the space generated by two elements. So U alpha is a two-dimensional space. So when we look at U alpha plus U alpha star, we are working on a four-dimensional space. So to describe these invariant generalized complex structures on a flag manifold, for us, it's enough to describe the possible invariant generalized structures on U alpha, which means that we are looking for endomorphisms J on a four-dimensional space satisfying three conditions: that J is a complex structure, which means that J squared is -1. J is orthogonal, which means that satisfy this condition with respect to that bilinear form that we defined in the first day, or equivalently, it means that satisfy this condition here, where B is the following matrix is 0, identity of order 2. Okay, all blocks of order 2 here. Is equivalent because when we consider the base of U alpha, which is A alpha and S alpha, and the dual bases, when we compute the matrix of the bilinear form that we defined in the first day, this will be the matrix of that bilinear form in the basis of this space here. Okay, this is why this condition is equivalent to this one. And we need J to be invariant, and invariant under the isotropy representation, which is equivalent to the adjoint representation. And more than that, since we are working with a maximal flag manifold, it's equivalent to the torus action, because we are working on a space. Where is it? on the compact real form under a maximal torus. So the adjoint representation will coincide with the torus action. Okay, so this is what we are looking for. So the endomorphisms on a four-dimensional space satisfying these conditions here. Usually, when I give a talk, I skip all the computations and I said, oh, doing all these demands, we have these possibilities. But today I will compute together with you how I will do all the computations to get the possible endomorphisms. Okay, so let J be an endomorphism. On a four-dimensional space. And we are going to denote J as a matrix, your matrix form, and we are use blocks because we are going to ask to satisfy this condition here. And here we have that B is a block matrix. So we will write J in terms of a block matrix where alpha, beta, gamma, and delta are real matrix of order 2. Okay? So first, we will ask J to be orthogonal. So J orthogonal. J orthogonal means that we need to satisfy the condition that J transpose times B is equal to minus B times J, where B is that matrix, that block matrix, okay? Where here are the identity 2 of order 2. Okay, I hope you don't get bored with all these computations. So let's do the computation here. J transpose times B. So if J is that matrix, so the J transpose will be given by this expression. And when we do this product, we obtain gamma transpose, delta transpose. Here we have beta transpose. Sorry. Oh, here's alpha transpose, and here is beta transpose. And on the other side, we have this. J is alpha, beta, gamma, and delta. So we obtain gamma, delta, alpha, and beta. So when we compare, when we demand to satisfy this condition here, we obtain the following, that gamma transpose is equal to minus gamma. We have that alpha transpose is equal to minus delta, and beta transpose is equal to minus beta. Here we have an equivalent condition of the second one. Okay, and it means that beta and gamma are skew symmetric, and we have that alpha transpose is equal to minus delta. So we obtain J has this form here, alpha, beta, gamma, and here we have minus gamma transpose, where beta and gamma are skew symmetric matrices. Okay, so the orthogonality gives us that J has this form here. where beta and gamma are skew symmetric. Okay, the second condition that we are going to ask here is J to be a complex structure. It means that J satisfies the condition that J squared is minus 1. Okay, so using that expression of J, we have that J square, let's compute what is J square. We have alpha square, alpha square plus beta gamma alpha beta minus beta alpha transposed gamma alpha minus alpha transposed gamma, and here we have gamma beta plus alpha transpose square. And we are going to ask J squared to be equal to minus 1, so it must be equal to minus the identity. Okay? And when we ask this, we obtain the following. So we have that alpha square plus beta gamma is equal to minus 1. We have that alpha beta minus beta alpha transpose is equal to 0, and gamma alpha minus alpha transpose gamma is equal to 0. Okay? If you look at the second expression here, we have alpha beta minus beta alpha transpose equals to 0. But we already know that beta is skew symmetric. So beta is equal to minus beta transpose. So this is equivalent to say that alpha beta plus beta transpose alpha transpose equal to 0, which is equivalent, using the property of the transpose, that we have this expression here. And it means that alpha beta is skew symmetric. It's also skew symmetric. And if you do the same on this expression here, we obtain that gamma alpha is also skew symmetric. Okay? Okay, but let's look what is. So let's look what we obtain when we of the expression of alpha beta. So alpha is any matrix of order 2, so it's A, B, C, D. And beta, we already know that is a skew symmetric matrix, so it's a matrix of this type here. Okay, then when we do the product between alpha and beta, we obtain the following. We obtain here dx minus ax and minus cx. Okay, we obtain this form, but here, from these conditions, we have that alpha beta is a skew symmetric matrix. So we have two possibilities. Okay, beta can be 0, then this matrix is 0, and we can have that beta is non-zero. And when beta is non-zero, we must have the diagonal 0 and this guy equal to this guy here, because alpha beta is a skew symmetric matrix. So when beta is non-zero, we obtain that x is non-zero, then b and c must to be 0, and we have that a is equal to d. Okay, so we obtain these conditions. So when we replace these guys on the expression of alpha, we obtain that alpha is actually of this form, A00A, which means that alpha is a scalar matrix. It's a real number times the identity. Okay, so basically what we have so far is, and well, if we use this expression here, that gamma alpha is also skew symmetric, we are conclude the same, that alpha has this form here when gamma is non-zero. Okay, so far we have the following. So we have, if actually I proved on my thesis that if beta is 0, then gamma is also 0. Okay, I will not enter in this detail here, but we have, if beta and gamma is 0, then the expression of J is just alpha 0, 0, and minus alpha transpose, where alpha square is minus 1. Minus 1 because when beta and gamma are 0, from this expression here, we obtain that alpha square is minus 1. Okay? And if beta and gamma are non-zero, then we obtain that J is of the form a scalar matrix, beta, gamma, and minus this guy here, where beta and gamma are skew symmetric matrix. Okay. So this is what we have when we ask J to be orthogonal with respect to that bilinear form, and J to be a complex structure. So J square is minus 1. So it remains to one condition to ask here. And the third demand that we are going to do on J is that J is invariant. And invariant, we mean invariant under the isotropy representation, which is equivalent to the adjoint representation, which we saw that is equivalent to the torus action. Okay. So consider T the group of the matrix, the matrices of the following form. We are called it block matrix, where this RT matrix is actually a rotation matrix. Okay, why we are going to consider this group T here? Because remember that I said that the adjoint are, since we are working with the space plus its dual space, the adjoint representation here is adjoint plus coadjoint. So when I say that it's invariant under the torus action, is an S1 here on the vectorial part and an S1 on the dual part. So it's basically an S1 times S1. This is why we are considering this group here. So the torus action, but the torus and the vectorial part and the torus, well, it's block, okay? So J will be invariant under the action of this group here if so. J is invariant if J commutes with the matrix, all the matrix K. So if satisfy the following condition, which commutes, which is equivalent to satisfy this condition here. Okay, so J will be invariant if and only if commute with the matrix of the group T, which is equivalent to satisfying this condition here. Okay, so okay, we have two expressions for J. J can be when beta and gamma are zero, we have this type, and when are non-zero, we have this type. But for now, I will consider J as we had before, just like this. And then after doing the computations, we see what happened when beta and gamma are zero and non-zero, okay? Just to do one computation and not doing a computation case by case here. So consider J like this. So let's see what happened with K, J, K minus 1. Okay, so K is given by a block matrix. So do the product here, we are going to obtain just the product in each block like this. Is a G, RT, beta, RT minus 1, RT, gamma, RT minus 1. And here we have RT minus alpha transpose RT minus 1. Okay, we have this expression when we do the product of block matrices. But remember that gamma and beta are skew symmetric. So if you do the computation by using this matrix RT here and using a skew symmetric matrix, you see that it will commute. So we will obtain, actually we will obtain that RT beta RT minus 1 is equal to beta, and the same when we replace by gamma. Okay, so we obtain this guy here, sorry, minus 1 RT minus alpha transpose RT minus 1. So if we want J to be invariant, J must satisfy this condition here. So this matrix here must to be equals to J. So must be equal to this matrix here. So J will be invariant if we have that RT alpha RT minus 1 is equal to alpha. Since beta and gamma are skew symmetric, they commute, so we have these guys here. So just remain these two entries. Okay, so J will be invariant if it happens. So J is invariant if satisfy this condition here. Okay, now it's the point on we split the case, right? When beta is 0 and beta is non-zero. So if beta and gamma are non-zero, we saw in here, when beta and gamma are non-zero, we saw that alpha has this form here. So it's a diagonal matrix. So diagonal matrix will commute with RT. So alpha is diagonal. which means that satisfy this condition trivially. It's okay. And there's the case where beta and gamma are 0. So if beta and gamma are 0, we have that alpha is an arbitrary matrix of order 2. It's a matrix like this. Okay? And when we ask to satisfy this condition here, I think you are already bored with so much computation, so I will skip this. So if we ask, RT is given by this expression. RT is a rotation matrix. So when we do the computation RT times alpha times the inverse of RT, we obtain that actually alpha has this form here. A minus B, B and A. Okay, just do the computation with the rotation matrix. So alpha must to have this form here. But remember, when we are asking that J squared is minus 1, we obtained that where is it? Here. We obtained that alpha squared is minus 1 because J squared must be minus 1. So if we compute alpha squared and ask alpha squared to be minus 1, so using the fact that alpha squared is minus 1, we obtain that alpha actually is equal to 0, minus 1, 1, 0, or 0, 1, plus or minus this expression here. Okay, so alpha must to be this matrix 0, minus 1, 1, 0, or 0, 1, which is equivalent to say that it's plus or minus this expression here. Okay? So, in resume, summarizing all these we did, therefore, we have that J is of the form. So J can be of the following form. When beta and gamma are 0, alpha must to be plus or minus this guy here. So it will appear here plus or minus 0, minus 1, 1, 0. Beta is 0. Gamma is 0. And here appears minus the transpose, which will be the same guy here. Or when beta and gamma are non-zero, we have that alpha is a diagonal matrix, so it's A, 0, 0, A. Beta is a skew symmetric, so it's 0 minus x, x, 0. Gamma is also skew symmetric. And here we have minus the transpose. So, and I didn't write here, but here we need to analyze this condition here, J squared minus 1. When J squared is minus 1, we have this condition, and it's translated in these guys here. We have the following condition, that A squared is equal to xy minus 1, okay? Because J squared must be minus 1. So after doing all this boring computation, we obtain that an invariant, an endomorphism, which is orthogonal, invariant, and satisfy J squared is minus 1, so J must to be one of these two forms here. Okay? So the problem, so just to give some names here, if you remember the examples of the first day, when we have a complex structure, we can define a generalized complex structure that we call J of J, and the expression is given by this. And observe that this matrix here is exactly of this form. And actually, we have that this guy here comes from a complex structure. So I give the name for this type of matrix, this complex structure of complex type, because it comes from a complex structure. Okay, so this will be called complex type structure. And this does not come from a complex structure, so it's called of non-complex type. Okay, so what we obtain of all this? Remember that I said that by that proposition, every invariant generalized complex structure on a flag manifold can be decomposed in blocks like this, where we have as much blocks as positive root and the Lie algebra, in the Lie algebra. So the idea was to describe each of these blocks. So we did it. And so to construct an invariant generalized almost complex structure on a flag manifold, it's just you combine these structures of complex and non-complex type, the diagonal. So you can have complex type, non-complex type, non-complex. I mean, you can, you have a lot of combinations here, but yeah, that's it. The generalized almost complex structure is completely described by these guys here, complex and non-complex type, and then you can construct a global structure just combining complex type and non-complex type arbitrarily.
Carlos,
Okay.
Carlos,
Yes.
may I ask you something?
Yes, sure.
So can you show the forms of the possibilities? What would be the symplectic type?
Yes, the symplectic time occurs exactly when A is equal to 0 here in this
Okay.
non-complex type. When A is equal to 0, we recover that form. The example of the first lecture was, if I'm not wrong with the signs, is like this. And
But
when A is equal
also,
to
yeah,
yeah,
x, y equal to 1. Yeah.
exactly,
Okay.
yeah,
Yeah.
you recover the symplectic form. Actually,
Great.
in a joint work with Elizabeth Gasparini and Fabricio Valencia, we proved that actually this non-complex type is always a bit transformation of a symplectic type. So we have complex type and a bit transformation of a symplectic type.
Oh,
These are
interesting.
yeah.
Okay, thank you.
You're welcome. Yeah. So this is how we describe all the invariant generalized almost complex structure. So in the next lecture, the last lecture, we will see how the integrability affects this combination of complex and non-complex type. Okay, so I will stop here. I think it's enough for today. It was long computations. Thank you.
Thank you, Carlos. I have only one question, but a simple question. We had there 4 equations about alpha squared plus beta gamma.
Yeah, here.
The first one is equivalent. And the
Yes, this will be equivalent with this
equivalent.
one.
Okay.
Yeah,
Okay.
because it's just the transpose
Right,
of alpha.
transposing. Yeah.
Yeah.
Okay. So, any questions, comments? Okay. So let's thank again, Carlos. Our next lecture will be on the